Hello everyone. So today we are going to see the simulation of recently developed grid forming control technique, that is Androff Hop oscillator based virtual oscillator control technique. So let us begin the simulation. So this is the layout of simulation. So here we can see that on the right side we have power references, and we are changing the power references at time t equal to 3 seconds, and this is Q reference, and this is going inside the inverter, and we have DC link voltage. So we have all set the parameters, and we have kept in the script MATLAB script file, and now we having the output of inverter. So inside this we have controller, inverter, and this LCL filter, and output of this inverter we have this bus where we have named it as VABC bus 1, IABC bus 1. Voltage and current are named accordingly, and then we have this distribution line, and then at the output we have again one bus that is connected to the grid. And here and this side we can see this uh, and below side we can see that there are various scopes and display are present to see the simulation results. So let us go inside the controller technique for this inverter and LCL filter. So this is the overall schematic for this inverter control. So we have used this universal bridge for this grid forming control technique. So first, one of the advantage for this grid forming control technique is that it is based on this instantaneous value. It does not require any phasor quantity for the closed loop control. So here we are taking only one reference, that is I inverter ABC. So this is the current reference that is we are taking just at the output of inverter. So what we are going to first do is that we are converting this current value into this alpha beta component into orthogonal signals. Then after that we are taking this instantaneous alpha beta current and providing into the rotational matrix that is present inside that. So rotational matrix are being compared, the this instantaneous value of current in alpha beta are being compared with this reference value of alpha beta, that we see how we are getting this reference value of current from this virtual oscillator control being compared, and it is being provided to the rotational matrix. So here in this MATLAB function we have written this rotational matrix. So here you can take phi equal to pi by 2 or phi equal to 0. So if you take phi equal to pi by 2, that is conventional, that follows the conventional regular truth. If you consider phi equal to 0, then it is just reverse of that, and that is we call it as reverse truth. So phi equal to pi by 2 is taken for this high voltage or transmission system, and phi equal to 0 is taken for low voltage, that is for distribution side. So this is for this rotational matrix, and after getting the output of rotational matrix, this is passed through this current gain values, and that provides the input to the virtual oscillator control. So E1 and E2 are the virtual inputs for the virtual oscillator control. So now we got the E1 and E2. So for this virtual oscillator control, we required a state dependent voltage and current sources. So how we get this state dependent voltage and current sources? So I have written down the equations. So you refer these equations for a state nonlinear state dependent voltage and current sources by following these two equations. So after that, after getting the input signals, so here you can see that electric schematic where we get the input signals for this virtual oscillator control after passing through this rotational matrix and getting amplified with this current gain, and after that we require this state dependent voltage and current source. So after applying these equations in this MATLAB, we get the Vm and Im, that is a state dependent voltage and current source. So I have implemented through this block diagram. So you can use the mathematic you can use either this MATLAB function, or you can either use this directly using the MATLAB blocks. So inside this MATLAB function, I have written down this VC square plus epsilon naught IL square. That is nothing but that are the states for this virtual oscillator control. So we require these things to get the Vm and Im, that is state dependent voltage and current sources. Now after getting the state voltage Vm and Im, then we can have we can apply this dynamic equation for this AHO based VO control through this one. So we know this oscillator circuit dynamics corresponding to inductor current and capacitor voltage for this virtual oscillator control is written like this. So after applying VL equal to L di L upon dt and IC equal to C dVc upon dt, and substituting Vm and Im from the previous slides, we get this equation. So we have applied this oscillator circuit dynamics here in this MATLAB. This one, if you see, this one is the oscillator state circuit dynamics. So you will get this VC and IL, and after passing through gains like voltage gain and here epsilon and voltage gain, you will get the corresponding reference voltage in the alpha beta frame. So we got V reference alpha and V reference beta. So after getting this V reference alpha and V reference beta, we need to get this current reference values. So how we will get this current reference values? So we know we require this reference values of powers. So earlier I told you that we are providing the power references from here. So from this power references we get, so from this power references we apply this reference current generation. Here you can see reference current generation from these powers. We apply this equation here inside this current reference subsystem. So we have applied just this expression, and we will get this reference values, current reference values in alpha beta frame. So after getting this reference value alpha beta frame, we again goes to compared with this instantaneous alpha beta current and pass through this rotational matrix and current gain values, and that will provide to the input to this virtual oscillator controls. So now we have understood this how we are generating the references alpha beta values for this virtual oscillator control. So now we need to convert this reference alpha beta values into this AVC uh, natural reference frame. So we have converted in alpha beta component to ABC reference frame, and now we are generating the PWM pulses with the help of this PWM generator. So we have used these 3-phase bridges, that is 6 pulses, and we are getting the PWM pulses for this inverter. So if you run the simulation, so let us see the output. So this is the voltage and current at the output of converter, and this is the voltage and current at the output of distribution line. So we are changing the power references at time t equal to 3 seconds. So here you can see that this voltage remains stable when we are changing the current references at t equal to 3 seconds. So this controller works fine, and you can also see the frequency response to see how its response is faster as compared to the phasor domain based control technique. So you can see the RMS values that you can see that we are giving the power references before t equal to 3 seconds 6000 and after t equal to 3 seconds 8000. So you can see that our power reference is getting changed accordingly. So earlier it was something 6500 and after that it went to 8500. So you can say that it varies its power according to this power references. So that's all. Thank you. I will provide you the a script file in the description, means all the data for this simulation in the description. You can refer from there. Thank you.